Okay, last lecture we looked at normal incidence of a plane wave on a boundary between two uniform mediums, right? We didn't quite, we have a little bit more of explanation or interpretation to do with this, and then we'll get into the next case, which is a layer. So this was actually very easy to solve. We didn't really need the explicit expressions here. We just imposed the boundary conditions, used the specific acoustic impedance, and we found, inverted this, found the reflection coefficient. You can use either one, either form here, they're mathematically equivalent. And from that, with a boundary condition, we've got the transmission coefficient. So those involve the amplitudes, like pressure amplitudes. That's how they're defined. Usually more important is intensity or energy. Here's the intensity reflection coefficient and the intensity transmission coefficient we also found. We confirmed that energy is conserved here. If it wasn't, we would have made a mistake. And we started to look at some special cases, where the specific, the ratio of the impedance is equal to or greater than 1 or equal to 1. When the same wave impedance occurs in both mediums, you got no reflection, which is good in some practical situations. We did a demo, and I'm going to skip this. Now I want to continue, and I want to point out here that I can't remember how much you do in 3119, but this is very similar to waves on a string under tension. I don't think you go into this depth. I can't remember. But it's very similar. And however, there is a difference here. You want to remember from the last chapter that the impedance has the form of the square root of the stiffness times the inertia. Now, different mediums, different types of waves are going to have different stiffnesses. There'd be a different mathematical form for this and a mathematical form for that. But the idea is the same. So in waves on a string under tension, what plays the role of the stiffness is simply the tension. And the inertia, is the mass per unit length, right? So if you imagine having two strings here, they're going to be under the same tension, right? So the stiffness is going to be the same. So if you want to have no reflections, if you want to match the impedance, you have to have the same mass per unit length. So it's trivial in that case. You have essentially the same string, the whole length here, and you're not going to get any reflections. So for the case of wave strings, they're not quite as general as the acoustic case here. However, the torsional wave system, remember, I better stay away from that right now. Remember, way back in the beginning here, where is it? There. We hooked up these two torsional wave apparatus. This is the top view. Now, in the manufacturer went with the same steel rod here and here, same size. And then the inertias are different, right? So there will definitely be an impedance mismatch here, and sure enough, you saw reflections. However, you can imagine that as a wave, let's say the wave is traveling here, you can imagine matching the impedance here. What's one way of doing it so that there are no reflections? You have greater inertia here, right? You got to keep the product the same. So,
greater stiffness on the left.
Right. You would have you could use a rod of a specific thicker diameter, bigger diameter. It would be a specific, you can solve for that. And in that case, you should get no reflections. And it doesn't matter, of course, which way you're going. An alternative is to, wait a minute. What did we say here? Wait a minute. We've got greater inertia here. Yeah, we want the diameter to be less here. We want it to be less stiff, okay? Now, it's a little counterintuitive, and the reason is we're all thinking the same thing, including me. We just naturally think speed of sound here. It's not the speed of sound that we're dealing with here, right? It's coming up eventually. That goes like the inertia divided by the stiffness. This is a different quantity, the impedance here. So it turns out you want to, because of that greater inertia, according to this, to match the impedance, you want less stiffness, so you'd have a smaller diameter. Alternatively, you could make the diameter on the left side greater to balance that less inertia there, either way. Okay, now, there's another way of doing this. Some people sometimes do this, is here's the torsional wave apparatuses that we dealt with last lecture, right? And what's in between here is this another torsional wave apparatus where there's a continuously changing inertia. It takes you from the high inertia here down a factor of 2. That's not right, it's a factor of 4 because it goes like the square. So it takes you down to this inertia here, right? So what do you think the point of this is? In fact, what do you think this is called? Take a wild guess. An impedance matcher, right? So if we have a wave, we're going to do a pulse, of course, here. If we have a pulse here, and it comes down here, if this is slowly changing, in this region, in the non-uniform region here, if it's slowly changing compared to if the wavelength is small compared to this typical distance here, the wave will be seeing a slowly varying impedance down to here. So we would expect very little reflection, right? On the other hand, if we have a long pulse here, if it's very long, which we can't do, unfortunately, here, but if you have a long one, you come and what it's going to see is almost as if this is not here. It'll be abrupt, and then you'll see reflections and transmissions. So we really can't do the long wave. Let me try to do a longer, that's kind of about as long as I can do. So you see we get good. It's good here. Did you notice that? There's very little bit of reflections here. But we got some here, and it's really pointing out a problem here. Let me show you the problem. I'm going to go to a short pulse now, okay? Now, what you see here is, it works well here. Here, there's a reflection. There's clear reflection. Let me do it again. And that really shouldn't, I don't think that should be there, but does anybody see why it might be there? Take a look at their apparatus here. Here's a hint. This one has been used a huge number. People seldom get this one out, okay? But they use this one a lot. Look, what's going on here?
Space.
Yeah, the rods have fallen off, okay, due to heavy use. And in fact, we're missing 2 rods here. We have a discontinuity here because we're missing those rods. Now, normally, I don't, and that may have caused some slight problems with the demonstrations last lecture. I haven't done this in a very long time. Normally, we don't do it, but I decided, because we're videotaping this, I decided to do this demonstration. But it points out the fact that I got to get this fixed. We've got the bars. You know, they fell off, we kept them. Some of these bars are actually loose, too. Look at this one. This one needs to be re-welded. It's loose. So I'm going to have this fixed, and it should be better. Okay. Okay, any questions about that? Okay, so let's get back to our acoustics here. And we want to look at some, again, look at some special cases. If you look at the intensities, okay, that we have, the reflection intensity and the transmission intensity, it's not difficult. In fact, you can do it in your head. When you have an extreme mismatch in impedance, and it doesn't matter which way it goes, the incident medium could have a much greater impedance than the transmitted medium, or it could be much less, or it could be much greater. It doesn't matter. You will see that you get very small transmitted intensity, which means you get a lot of reflection. You can look at either of those expressions. You'll find this. However, I want to point out, and I fell into this trap in the problem discussion, is this only holds for intensities, which is usually the more important thing. If you look at amplitudes, it doesn't quite do all this, okay? So the statement here is that with respect to intensity, which again is usually the more important quantity here, when you have a big impedance mismatch, almost all the energy is reflected. And it doesn't matter which way it goes. You could be seeing a much greater impedance or much less. It's just the mismatch. And this happens for all wave systems. I mean, I think it's going to hold for all wave systems, and holds in electric circuits. Some of you may be familiar with that in electric circuits. Sometimes impedance needs to be matched there for an amplifier, for example, to get the power out. There's one more thing. I don't expect you to completely understand this, but it will come up later and in the next course, in the underwater acoustics course too. But it'll come up in this class. There is a difference between the two extreme impedance mismatches. When the incident medium has much less impedance than the transmitted medium, you can think of it as being very dense. You get, because of the high impedance, again, as a special case, you can think of it as very high density. You get very little particle motion there, okay? So the boundary is behaving like a rigid boundary. It's like you replace the incident medium with a boundary that just doesn't, that has infinite stiffness. It just doesn't compress or expand, okay? So that's a special case. We call it a rigid boundary. The other special case, when the transmitted medium has much less specific impedance, it's like there's nothing there. You have a pressure. The acoustic pressure is zero at the boundary. So the wave is pushing against a medium, but the medium has such low impedance that it's like it's not there at all. And we call that pressure release, where the pressure is zero. Now there's one final thing here that you wouldn't notice. Nobody would expect you to notice it unless you've encountered this phenomenon before, and most of you have not, almost all of you. All or almost all of you have not, but we're going to go into it in depth in the next chapter, is this interesting fact here. So here we have medium 1, medium 2, right? Medium 1, medium 2. Here we have the incident wave coming in from medium 1. Some of the energy is reflected, some's transmitted, right? Here, we've put the source on the other side, so now the incident wave's coming in here. These are different situations in general, but they're intimately connected in a way that's not at all obvious, but it's universal. It's everywhere in nature, and not just in waves, it's everywhere. It's called reciprocity, all right? And we're going to, I don't want to say too much about it now because we're going to go into it in depth in the next chapter, as I said. But we can see it in our expressions here. If you look at the expressions, you can show, and again, we don't want to get into it, we just want to look at it kind of superficially right now. You can show that I'm using the primes for the second situation, the one on the right there, okay? You can show that if you take the incident pressure divided by the transmitted particle velocity, these amplitudes here, from the waves coming this way, that ratio is the same when it's coming the other way. Okay? So the usual way that this is stated, simplified, is suppose you have the same pressure. Which is not unusual. You know, you have a driver here. You're generating certain pressure. You move the driver to the other side, to the other medium. Well, let's assume it has the same pressure amplitude. In that case, these two p's cancel, and what do you conclude? That the particle velocities are the same. So the way we think about this is the pressure is the drive, the velocity is the response. This is a kind of impedance here. Actually, the transfer impedance, as we'll discuss in the next chapter. But there's this interesting property, and it turns out to be universal. I mean, it's just everywhere. But many people don't know about it because it almost always comes up in more advanced studies. You got a drive in a medium here, and it turns out to be very general. We've done it in the case, you know, I'm getting in trouble here. We did it in this case, but you could have a continuously changing medium. You have a drive point and you're picking up the response at another point. If you swap the two, if you switch the two, you get the same response here, no matter what's in between, no matter what it's doing. It's remarkable and not obvious at all. That's called reciprocity. So we're going to go into this in much more depth in the next chapter. But I just want to point out to you that it's already in. You know, it's in our simple problem that we're doing here. This problem right here, there's reciprocity in there. Okay, any questions? All right, so we're going to spend the rest of the time on the layer problem. This is normal incidence on a layer. This has a lot, you can probably imagine, and you'll see, there's a lot of applications here, important applications. So we have a normal acoustic wave coming in, not oblique. That turns out to be, we're not going to touch that with a layer. We'll do the oblique with two mediums. That'll be tomorrow. But oblique here gets really complicated. This gets very complicated, as you'll see. We have normal incidence, and we're going to do, it's important here to do the general problem of three arbitrary mediums here. Three is not necessarily the same as one, okay? Although in practice often it is. But we want to be more general here. So we're going to look at the steady state motion. When you start off with this being quiescent here, you turn on a drive, there'll be transient motion, transient pressure, acoustic pressure and particle velocity. Eventually, for a constant frequency drive here, the system will settle down into its nice steady state. There'll be a constant amplitude of the transmitted. This pressure comes in here. There'll be a constant amplitude of the right traveling wave. There'll be a left traveling wave. It'll have constant amplitude. There'll just be a right traveling wave here, because we're assuming nothing's coming in from infinity. Here we have to deal with both. In general, there's going to be reflections there. So here are the expressions for the right and left traveling waves. You see the minus sign and the plus sign. And we've gone to, everything's at the same frequency, and I'll comment on why that is as we'll see it explicitly here. And we have these amplitudes here. Okay, and we're conveniently using complex phase factor. Otherwise, nobody wants to solve this not using complex numbers. So what do? Well, we have to impose boundary conditions, like we did before. And then we want to recognize the specific acoustic impedances for each of the three mediums. Now, there's a difference here. Before we lucked out, we didn't have to actually use the expressions for the single interface case. Remember that? We just were able to form the impedances we wrote down the boundary conditions. Oh, and what are the boundary conditions? The pressure, the instantaneous acoustic pressure has to be the same on either side, immediately on either side here and here. And similarly with the acoustic particle velocity, to be the same. So here we have to use these expressions. It's just not as, it's more complicated than the previous case. So what you do is you set the pressure, the instantaneous pressure. The total pressure on the left side is the sum of these two pressures. All right, so you're going to get something that looks like this. You set it equal to the sum of the pressure over here, right at the boundary. The phase factor goes, x is equal to 0. So that goes. There'll be an e to the I omega t. But because there's an e to the I omega t on each side, it cancels. And that's the explicit proof that why the frequencies can't be. You have to have the same frequency here as you have here. If you don't have that, you won't be able to cancel out and won't be able to find a solution. The solution doesn't exist. What I've done here is I've equated because the pressures and the particle velocities are the same, the impedances have to be the same. So what I've actually done is I've formed the impedance here, the pressure divided by the velocity. But I've used these facts in here to reduce this down. So I've done, there's a fair amount of algebra that's been here. It's not real complicated, but there's some algebra that's been done here. We don't want it would take too long to go through the algebra. And it gets much worse than this, incidentally. This is actually pretty simple. You can sort of see what's going on here in your head. We do the same thing over here, but now we have an e to the I, x is equal to L. So we have an e to the I KL. And K is different in general on either side. So that's why you'll see the complex phase factors there. So we have two equations. Two complex equations. How many unknowns do we have? How many complex unknowns do we have? No, not 4. It looks like 4, doesn't it? But what if I divide numerator and denominator by a here? What do I get? I get b over a. That's all that I get. If I divide by the incident pressure, I get PR over PI. There's really only two unknowns here. And this is because it's a linear system. All that's important is the ratio of the pressures, the ratio of the reflected pressure to the incident pressure, the ratio of the right traveling wave, the left traveling compared to the right traveling. Usually we think of this as B over A, but it doesn't matter. So you have two complex equations, two unknowns. They're linear equations. You multiply the denominators out. They're linear equations. They can be solved. Okay, it's not easy. It's messy. Okay, but you have two equations, two linear equations, two unknowns. Then you eliminate one of the, you find one of them. We're going to go for, we'll go for the reflected pressure divided by the incident pressure, because that's the definition of the reflection coefficient, remember? So I think the first time I taught this course, I verified the algebra. I haven't done it since then, and I'm not going to do it. Okay, because I remember it's a substantial amount of algebra here. Okay, so we're just going to quote the result. But I remember feeling, well, I better, even though the book is in its 4th edition, there's still mistakes in the book. Okay, and we're going to encounter one in this chapter. Now, these aren't trivial mistakes. These are fundamental mistakes. So I did confirm that this is right. Now, this is a whole lot more complicated than the case we did previous lecture with just one interface. For one thing, you'll notice here, before the reflection coefficient was real. Okay, it was either positive or negative or 0. What about here? You see the I right there? It's complex. But we would expect this. The reason we would expect it is, this means there's a phase, a non-zero, the phase between the reflected pressure and the incident pressure at this interface right here is in general neither 0 nor 180, as it is for the single interface case. And the reason we'd expect that is this pressure wave coming off here is going to be influenced not just by what's going on here, but what's going on here. This wave comes here, some of it bounces off, comes back here, some of it gets transmitted. It's going to change the phase of this reflected wave here. So that's why we have, it's complex now. And this is why you really want to use complex numbers here, because the amplitude and the phase are dealt with in a unified way. That's why it's really good to use complex factors here. We didn't really need that. We didn't use it previous case. Okay, now I should point out, and I'll let you do this if you're interested, but this is actually a generalization of our previous case. For example, what if L is equal to 0? We got back to the other case, except we're calling this 3 before we called it 2. That's true. What's another way? What's another thing we can do here to get the special case? It's easy. What if this medium is the same as that medium? We're back to the other case. And then what if this medium is the same as that? Then we're back, okay? So we have several checks that we can do here. And we won't go through this, but I'll tell you, I've done it. You can do it if you're interested. If you do take these special cases, you could do the L equals 0 in your head, okay? You can see it. L is equals 0, these are gone. These are 1. That's what we got before. Okay? And you can do it similarly with the other way of looking at it, other ways. I guess to be complete, I should have said also R1 equals R2. That's another way. Okay, well again, what we tend to deal with here almost always is intensity. It's usually what you're interested in. So for normal incidence, you remember the intensity reflection coefficient is just the square modulus of the reflection coefficient. Same medium. That's easy. The transmitted is can get complicated because it's a different medium. So we avoid that, and we just use energy conservation here. We know that the power the power coming in, whatever percentage is reflected, 100 minus that percentage has to be the reflected, the transmitted power. And we know that the intensity coefficients have to be identical to the power because we don't have that dissimilar area. We have normal incidence when we talked about that in the first lecture on this. So, having found the reflection coefficient, we can find the transmission intensity, or an intensity transmission coefficient, simply by taking 1 minus the square of that. I shouldn't really say simply. This looks simple, but when you do it, and again, I think I did it once a long time ago, you get this following expression. It's messy. Okay, but it's exact. So it holds for all different possible situations that you can imagine here. So the way we look at this, to appreciate what's going on, is we look at special cases. And in fact, that's what usually happens when you're in any realistic situation. Almost always, there's going to be some terms that are negligible here. You're going to be able to make approximations. It's just, there's a huge parameter space here. Well, I guess the parameters are basically we got dense, So the parameters of the density and the impedance. Or the way we do it is the speed of sound. And the speed of sound is here because of these Ks right there. So we really have a pretty big parameter space here. And if you just start looking at some experiment, you're not going to be in the most general case where you have to include all these terms, okay? Or you can't make approximations. So that's what we're going to do, and there are 4 cases we're going to look at. And again, typically, in this big parameter space that you have, typically when you look at any situation, random, or it could be practical or not practical, typically what you're going to find is that there's just a lot more parameter space to have low intensity or high intensity transmission. That's typically the case. So that we're going to see that now. You'll see this. So the first case, which is pretty obvious to do here, beyond the trivial cases of one interface. We talked about it, this medium is equal to, we talked about that, right? Those are trivial. The first case that we're going to do is this fluid being the same as that fluid. R1 equals R3. And C1 equals C3. Okay, so we're going to look at the more important is in this case is usually often you're after sound insulation here, and you want to cut down on this intensity transmission. So we're going to look at this expression here. And if we set R1 equal to R3, okay, you can see these factors here simplify, okay? And then we'll go for we'll deal with the sign of K2L. So we'll replace the cosine squared with 1 minus the sine squared. And you can actually do, if you stare at this, you can do it in your head. Here's what you get. A big simplification, right? But it's still not all that simple to get a physical appreciation for what's going on. So we can as you'll see, we can beat down on this even more. So here's some possible applications. You have a solid boundary between 2 mediums of air and 2 mediums of water here. So this is the R1 equals R3 case. That's what we specialize to in this expression. Now, typically, and I'm not going to do any numbers for you right now to prove this, but we will in one case. It takes a little effort, and we'll do it in one case here, and we'll do it in the problem set too. I distinctly remember that. But I'm just asking you to accept this. Well, I think you'll accept this fact. Typically, this is typically a solid material. Doesn't have to be, but typically it is. And the specific acoustic impedance of this is typically much greater than here, okay? Now, when you get to water has a pretty high impedance, so you want to be careful, and we'll confirm that numerically. But it turns out also to be typically true that the specific acoustic impedance is greater, much substantially greater. So we can make that, that's going to allow us to approximate this, as you'll see. There's another thing, though, that's typical, and that is, if you look at this K2L, okay, K2 is 2 pi over the wavelength in the medium here, in the layer, right? Typically, the wavelength in the layer is substantially greater than the thickness of the layer. We call that a thin layer, okay? When the wavelength is much greater, and that's typically the case. Typically, these layers here are not thick. And it's because in a practical situation, you don't want to make them thick. You only make them thick when you have to. And in some acoustic chambers, some reflection chambers, they will use 1 foot thick concrete. I don't know what we have a small one here, just down the hall. They're also called live rooms or echoic rooms. Okay, this is where you get good reflection off the walls. The one that I was used to, where I went to graduate school at UCLA, they had 1 foot thick concrete. It was a very large chamber. I don't know what ours is here. I don't know if it's 1 foot, but that's serious business. Usually this is going to be much thinner. Okay, so that's a good approximation we can make here. What's the sign of a small quantity in radians? It's equal to that quantity, right? So have we seen this before? Okay, it's just a Taylor expansion. And you remember, theta must be in radians. This doesn't work for degrees. And we'll do that. We'll see an example here, and we'll do problems in this. So you have to be careful about that. Okay, so what does that buy us here? Well, you can see here, because R2 is much greater than R1, this is going to be small, so we just keep this one. And we replace the sign of K2L with just K2L, and then you can see that we can write it like this. So, now this is interesting, and this is why we're spending almost a whole lecture on this. This is a complicated situation here. What do we have right here? Well, that's small, right? Well, what's that? That's big. So what's the product of a big number and a small number? What? It could be close to 0. It could be out there near infinity. It can be anything. So what we're forced with here is to now look at we've looked at a special case here, where R2, we've made 2 assumptions to get here. We've assumed R2 is much greater than R1, which is typically the case. Much substantially greater impedance here than the identical mediums on either side. We've also assumed that this is thin, right? Now we're going to look at 2 cases. What happens is, when you want to apply this to a situation, typically what happens is, one of these is going to dominate. So this is much bigger than 1. This is much less than 1. Usually one of them is going to win out. That's typically the case. So the first case we're going to look at, it turns out for a concrete in air, and again, we won't confirm this numerically, but we're going to do an example, and we'll do a homework for other mediums. In that case, you can show, by plugging in the numbers, going to the back of KFCS, you can show that the R2 over R1, which is big, beats out the smallness of this. So this quantity becomes large, much greater than 1, so we can neglect it, and now we get a simple expression, okay? And how much intensity is getting through there? What do you think? This is much greater than 1, what are we seeing? Good insulation, right? So there's very little. Now, you're going to say, well, that's obvious. Why are we going through this theory to do this if it's obvious? Well, we've quantified it here. We can say, and we're going to do an example, numerical example. We can say how much goes through, so we can actually calculate it here. Yeah, 1 is just a gross approximation. We know how it differs from 1. It's going to differ by a small amount from 1. We can calculate it. Okay. Now, here's the big deal with this. And one of the reasons we beat it down. Now we can look at this physically. This is the intensity transmission from air to air, right? Same medium. So the transmission coefficient is going to be, this is going to be identical to the square of the transmission coefficient. We don't have to worry about those factors in front because it's the same medium. We hit this with in general with the reflection coefficient. So the transmission coefficient, which refers to the pressure, to the amplitude, is just the square root of this. And look what we have here. This is proportional to the density of the slab, right? This is proportional to the width of the slab. So here's the rule. The rule is if you want to get good sound insulation in a situation like this, what you want to have here, assuming you have to check these approximations, but they're typically true. What you want here is a high mass per unit area, because the density, this material has a density. When you multiply it by this, you get the mass per unit area. You take the mass per unit volume, multiply by the area, you get the areal density. So we've come up with it's a pretty obvious fact that if you want to insulate sound, if you either want to prevent sound from getting out or prevent it from coming in, you want to use material that has a high mass per unit area, a high areal density. And unfortunately, people are playing around with exotic materials now called metamaterials that may eventually change this. But the way things are now, for a practical sense, that's about it. If you want to sound insulate, you need to have material with a high mass per unit area. There's lead. There used to be. We removed it. On one of our chambers here, it was shielded with lead, and that wasn't for electromagnetic radiation. It was for acoustics because it has a high mass per unit area. It was, I think, 1/4 inch thick lead, very heavy plates. So I remember reading about this in the New York Times in the 2000s. There were all these companies springing up around New York because New York is very, urban environments are very loud now. And so people just naturally want it quiet. And a lot of people do home musical recording. Most people, well, it used to be that most people played an instrument. Nowadays, I don't know. It seems like it's going down. How many guys play an instrument? One. Anybody else? Gene? Well, okay, Gene plays. Maybe several, at least guitar, right? I play guitar. See what I mean? One of the students, one of 8 students. Yeah, so it's unfortunate. I think it's really unfortunate. People have been playing musical instruments. They keep pushing it back. The latest I heard was 40,000 years ago. They find flutes that are 40,000 years old. Of course, they didn't have computers, so I think that's probably the problem here. Is, why should I play a musical instrument when I can just simulate it on it, and I can just listen to somebody else on a computer? Okay. Anyway. Okay, so it was pointed, there were these companies springing up in New York City, and people were surprised to find that, you just have to brute force this. You've got to have a lot of mass per unit area. They thought there was just some magical material that would work. But, no, maybe someday. Okay, now it turns out that a typical case for a solid panel in water, okay, and it's thin, okay, or for a thin membrane separating gas. I've actually done this in research. We'll talk about it when we see it. It turns out that the opposite occurs. In this case, instead of this dominating like it did for concrete, now it's the other way around. Now the smallness of this beats out the largeness of this. So now we have a small quantity, our one quantity here. We beat it down to one quantity. So now this is small, so now we get good transmission. And again, this is valuable because we've actually quantified it here. And we're going to, so now here's our numerical example. I think this is actually usually I would state it here. I think I got this from the book. I can't remember. This might be a problem in the back of the book, or I may have modified it. So here's the idea. We have some sonars producing underwater sound here. We don't want the sonar face to be exposed to the seawater. So this may be one reason that they do it. I don't know. This could be fresh water in here. So you have a, and this is commonly employed, I've read, that there'll be a, here's a dome, and it's filled with water. So the problem here is that we got this material. Let's not worry about the impedance mismatch here. Okay, we'll talk more about this next quarter. Okay, but we're just going to focus on the impedance mismatch due to the fact that you've got this thin layer of steel here. 1 millimeter thick steel wall. Yeah, I think I cooked this problem up. I remember cooking that up. Okay, so we're not going to make any assumptions here. The only assumption we're going to make is that we've got the same, you can forget this, we've got the same medium on either side of the partition. Okay, of the layer. We've got this layer here. So we're going to start with the exact expression when R1 is equal to R3. So I guess that's this. Right. So all we've assumed here is that R1 equals R3. So we're not going to make these assumptions that we did here. We're going to actually calculate the numbers. Okay, so here we go. What are the specific acoustic impedances for the water? You've seen this. You've used this before. For the steel, you look in the back of the book and you find it's this. So we have a factor of 50 difference. The impedance of the steel is 50 times. So that's pretty big. But I want to point something out to you here. If you go back and look at the expression, this is what occurs in the expression. Okay, this is a big number. This is a small number. What we're going to do here is we're going to neglect this term because R2 is much greater than R1. But I want to show something to you. You can express this like this, right? You can factor out this R1 over R. You can factor out an R2 over R1. So this is equal to this. So our approximation, what we're neglecting, is not really R1 over R2. We're neglecting the square of R1 over R2 compared to 1. So this 3% ratio here, our results are going to be accurate to the square of that. It's 0.1%. So this is a very good approximation here. It's much better than 3% because it comes in as the square. It's a very good approximation. When we do that, we get down to this. We've neglected the R1 over R2. Now, what about the, can we assume a thin layer? Well, we have to check. What's K2L? Can we make this approximation? It's nice. It greatly simplifies things. So what's K2L? Well, K is omega over C. We're in steel now. So, and we have a certain frequency, so there's a 2 pi. So we get K2L, which is a dimensionless number, is 0.0, it's about 100th. So we can make this approximation. That's good. We have a thin layer. So we make that approximation. And now the expression comes down to this. And now we're down to this other, we have this one quantity here. Remember this quantity? This is big, this is small. Which one wins out? Well, in this case, it's the thinness that wins out. This is a big number, this is a small number, but, and it's hands down, okay? It's 0.02. So it's nowhere near 1. So we're going to have good transmission here, which is a good thing because that's what you want in this practical case here, okay? But I want to point out to you here, somebody may say, well, yeah, if you have thin steel, if it's thin enough, you're going to have good transmission. Yeah, that's true, but we can calculate it here. We can calculate it. So if you're after a certain number, we can calculate how thin that steel has to be and if it's, whether or not it's acceptable or not for what it's going to be, what it's going to go through. So in the end, here's our intensity transmission coefficient. This is small compared to that, so we can, the 1 plus a small quantity, 1 over that is 1 minus a small quantity. So what we're seeing here is about 3% of the intensity is being reflected. We've calculated that. So we'll do a similar problem to this, like this, in, I guess, Thursday. Yeah, Thursday. Okay, so that was all case 1. Now case 2. Now we're going to have different fluids. This is a more general case. We're going to look at different fluids. And here, we're again going to look at a much greater specific impedance for the layer. We're going to assume it's thin, and we're going to assume that the thinness beats out the impedance mismatch there. And we get this. Okay, we can check this. The case we just did was R1 equals R3. And you can look at this and see you get perfect transmission in the limit there of these approximations. But now we've got different mediums. Okay, so we're getting some, 1 and 3 are in general different. So we're getting some, we're not going to get 100%. However, if you look back at what we did in the last lecture and replace this 3 with the 2, you'll see that this is identical to the single, to just an interface between mediums. So we can infer here that the layer is not doing anything here. It's as if the layer wasn't there. All right? Which again, maybe is obvious. I don't know. It depends, I don't know if this is obvious. And the limit, of course, is the layer. Well, I don't even know if it's obvious there. I better not get into this. But anyway, what we have here is that when you have 2 different acoustic mediums, you can put a boundary there such that it's acoustically transparent. You get very little reflection. The boundary has very little effect. Now, if the medium is different on either side, you're going to get reflection. But the layer will not be playing a role. And this is called acoustic transparency. Here's a classic example. You have a thin membrane here, okay? And you want to verify the numbers here, but this turns out to be, it's like it's not there. And this can be very convenient if you don't want these gases to mix. What I've done before is, I've had the same gas here, but it was a nonlinear experiment, and we had flow. We wanted to cut down on flow. High amplitude acoustics can generate steady flows, okay? And so we wanted to cut down on it, so we just used some household cellophane. It worked well. Okay, here's case 3. If you go back and look at the expressions, remember it has sines and cosines of this quantity? You'll notice that when you have an integral number of pi, things are going to simplify. The sines go away, right? And the cosines are equal to 1, and we get this nice simple formula here. Well, does this look familiar? Look what's on the previous. It's the same as that. So it's as if the layer is not there. Again, this is just good practical uses for this. It's as if the layer is not there. What does this mean, an integral number of pi's for this? Well, k is 2 pi over the wavelength. So what you can easily show here, and I just mentioned it here, is this corresponds to the case where there are an integral number of half wavelengths. The layer, the sound inside the layer is a half a wavelength, or 1 wavelength, or 3/2 wavelengths. It's an integral number of half wavelengths. And what's happening there is this. As you imagine a thicker layer, the transmission or reflection is periodic in the thickness of the layer. That's because we have these sines and cosines. So it's going to be periodic. And it's reasonable, and you can show with effort, that if you cut this down by half a wavelength, you're not going to change. Well, you can it's actually easy to verify. Excuse me. If you look at our expression here, if you take away half a wavelength here, like in this case, if you cut this down to here, you're not going to change. You're not going to change anything. And it's kind of reasonable from a wave reflection and transmission point of view, although that's not really obvious, but you could, at least it's reasonable, I think. So if our layer is a half integral number of wavelengths and we keep taking a half a wavelength away, eventually we end up with no layer, right? And we have the same result as before, as what we started with. So that's what's going on here. You can get acoustic transparency if the layer here is a half integral number of wavelengths. And what transparency means is that you don't have to have the same medium on either side here, but the layer has no effect. It's as if it's not there. That's the way you want to think of it. Finally, time's flown here. Here's the last case. Some of you might have heard this. This is popular in optics. Some of you may have heard of a quarter wavelength plate in optics, maybe. This analogous thing happens in acoustics. Instead of an integral number of wavelengths, an integral number of half wavelengths, now we're going to do an integral. This turns out to be an integral number of quarter wavelengths. And more specifically, what it is this. It's interleaved with the half wavelengths. So it's a quarter, 3/4, etc. So the half wavelength case is in between this sequence, right? The half wavelengths. In between here and here is a half wavelength, right? So it keeps going like that. Something happens in this case, and you can just easily see the mathematics. In this case, instead of the sine being 0 and the cosine being 1, now the sine is 1 and the cosine is 0. And then that causes a big simplification, and you get this expression for the intensity transmission coefficient. Okay? And now you say, well, okay, so what? Well, I don't know who discovered this, but if you set R2, if you dial up in your system, if you make the specific acoustic impedance of the slab the geometric mean of the two on the other side. So it's not R1 plus R2 divided by 3. It happens to be the square root of the product. That's called the geometric mean. I don't know if we talked about that before in this class. I guess it was the last quarter. Yeah, this comes up. There are different types of means out there. When you take this and substitute it in there, you get 1 exactly. So this is routinely used in optics to cut down on reflections for a coating. But it works for acoustics too. Now, I don't know of any examples, but I'm not really into this stuff. There's maybe some of our distance learning students know some examples of this, but it's the same idea here. So by coating something, you can get perfect transmission. Okay. Any quick questions?